So I'm going to tell you today about this project. Well, I guess it's a number of different projects, but the overarching theme is these infinite staircases in symplectic embeddings. So, so the first project that I want to tell you about, so where the story starts, is this project. I think this is actually the old name of the paper. It's now slightly different, but infinite staircases and reflexive polygons. But the reason why I have this, why I wanted to have this slide here, is to advertise this IAS Summer Collaborators Program. So these are Alessia, from left to right, Alessia Mendini, myself, Dan Christopher Gardner, and Tara Holm. And this picture was taken during this Summer Collaborators Program, which is a program at the Institute for Advanced Study in Princeton in the US. And it's for groups of collaborators to go work there. It's 2 to 5 people for 2 to 4 weeks over northern summer. So it might clash with, I guess, your teaching schedule a bit. I don't know how it is in the Southern Hemisphere, but I think the applications are for northern summer 2023 are in December 2022. So in a couple of months. But they pay for travel, accommodation, meals, and it's like a beautiful place. So I highly recommend. Okay, so that was my advertisement. So I should give a little bit of background. So what is symplectic geometry? It's a branch of differential geometry where you consider manifolds of even dimension, and the manifold has to have a way of measuring two-dimensional areas, so a differential two form. So the usual example is R2n with this differential form, which what it really means is that if you have, so how does this measure a two-dimensional area? If you have a two-dimensional surface floating in R2n, then you can think of the projections of this two-dimensional thing onto each of the coordinate planes. So the plane x1, y1, x2, y2, xn, yn. And on each of these planes, you have this shadow, this projection of your two-dimensional surface, and you can measure the area on each of these two-dimensional planes, and then you just add it all up. And that turns out to be like a non-degenerate area form. And it turns out that actually all symplectic manifolds locally look like this. So that's a theorem. So for other manifolds, you can just think of, if you have never thought about symplectic manifolds, you can just think that locally they look like this R2n with this form, but you don't even have to think that very much to understand the talk. So these are the objects, then the morphisms. So a symplectomorphism is a diffeomorphism that preserves the symplectic form. So if you do the pullback of omega-2, you get omega-1. And a symplectic embedding is a smooth embedding that preserves the symplectic form as well. So the first thing that I want to say is that a symplectomorphism always preserves the volume. So I guess I should say what the volume is. So if M is 2n dimensional, then omega to the power n is a 2n form, and it is indeed a volume form. So it is non-degenerate. Okay, so volume preserving means that if I do Rn, I get, so if this is a volume form in M2, this is a volume form in M1. Oh no. Sometimes the pen stops working. I don't really know what to do apart from why? No, sorry. I need to reopen this thing. Open with. Sorry, I was trying to fix this earlier today and just couldn't. So, share again. Maybe I should just share my screen. Okay. All right. Let's see if it works now. No. Yes. Okay. All right. So a symplectic morphism is always volume preserving, but not vice versa. So an example, maybe the earlier example of this phenomenon, or maybe the most important, is this Gromov non-squeezing theorem that says that if you have a ball of capacity R, so usually when people write this, they mean radius R, but of course, in symplectic geometry, you don't know how to measure lengths, and radius has a length. So you know how to measure areas. So you take like a two-dimensional slice through the center, and you measure its area, and that's the capacity. So that's the capital R. This would be R. So if you want to take a ball and embed it into a cylinder, this is the cylinder. If you only wanted your embedding to be volume preserving, you could just sort of stretch out the ball to be very long and thin, and then it would certainly embed into the cylinder. But if you want to preserve the symplectic form, you can't do that. It's so rigid that you need capital R to be smaller than or equal to little r. So you need to just be able to include the ball in the cylinder. So sometimes things in symplectic geometry can be very rigid, and sometimes they can be very flexible. Oh, there's a thing in the chat. Oh, I haven't moved the slide yet. Let's see. Wait, does that move?
Yeah, now we could see the second slide, but yeah, we were still in the first. You were just writing some things in the first slide. So
okay, yeah. All right. So this. Oh, okay. Yeah. Right. Okay. So that's a little bit of context about symplectic geometry, and now about this infinite staircases business. So there was a paper by Macduff and Schlenk in 2010 that was the first to introduce this idea, this phenomena of infinite staircases. And what they do is they calculate a function, C of A, whose value at A is the infimum of the size of a ball. So it's the smallest scaling of the ball into which you can symplectically embed an ellipsoid. Okay. So these are, I should say, from now on, all manifolds are four-dimensional. Okay. So maybe I should say why ellipsoids? It's because so a problem that was studied before this one, so again, in this thing of trying to embed things into other things, was if you have, for example, a certain number of balls, say 3 balls of capacity 1, and you want to embed them into another ball, what is the smallest scaling, the infimum size of a ball into which they embed all together? And people actually answered this. So, you can write a table for what the answer is. So if k is equal to 1, of course, that's like a trivial thing. It's just 1 because it's just the same ball. If you have 2 balls, you actually need the ball to be sort of like twice as big. So you're just like including them like that. But then if you have 3 balls, 2 is still enough. And if you have 4 balls, 2 is still enough. And then if you have 5 balls, you need to make it a little bit bigger, and so on and so forth. And then when you get to like 8, 9, and so on, it just becomes whatever the size has to be in order for them to all fit in terms of volume. So there's like no longer a like symplectic rigidity phenomena going on. It's completely flexible. You can squeeze those 8, 9, 10, etc. symplectic balls into this bigger one, and they will all fit and leave no space empty. Okay, so how does this relate to ellipsoids? Well, it turns out that this problem of embedding 3 balls into something is equivalent to the problem of embedding an ellipsoid of size 1, 3. So size, when you think of an ellipse in R2, you have like the great axes, which would be of size 1, 3, but here it's a 4-dimensional thing. So if you take these great slices, they would have area 1 and area 3. So embedding 3 balls of capacity 1 turns out to be equivalent to embedding an ellipsoid of capacities 1, 3. So this one would be called E1, 3. And so now you no longer need to think of this problem with this table, which is like a function defined on the naturals. You can now define this, think of this function as defined on the reals, on the positive reals. And so that's what they studied. That's what this function is. Here's the definition of ellipsoid, the definition of a ball, the definition of the function, which is called the ellipsoid embedding function of the 4-ball. And then this, this volume constraint here is this thing that I was saying about the very flexible behavior that is happening here at the end when you get to 8 and 9. That there's always a constraint, which is you can only fit as many balls or as big an ellipsoid, or alternatively, you can, your ball has to be big enough to contain the whole volume, because any symplectic embedding is volume preserving. So in this case, that volume constraint is given by the function square root a. Okay, and here's the graph of the function that they determined. And these lines are horizontal and the others are lines through the origin, which, by the way, the origin, of course, what is here as the origin of these axes is 1, 1, but the line does go through 0, 0. And so these lines are determined, because they're lines to the origin, horizontal. I could just give you the heights of each of these horizontal bits, and that will determine the whole function up to this vertical line. And so they are, the heights are 2 over 1, 5 over 2, 13 fifths, and then the next one is 34 over 13, and it continues up until that vertical line. So it might be that you recognize these numbers, or maybe you don't quite recognize them because half of them are missing. So let me write the whole sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. In those numbers, we have 1, 2, 5, 13, 34. So they're odd index Fibonacci numbers. So these stair steps are determined by odd indexed ratios of odd indexed Fibonacci numbers. Okay, so these are called the Fibonacci stairs. And then here, after a little bit before 8 onwards, the function just becomes equal to the volume constraint, square root a. And then here in between, there's a sort of fixed behavior. So by the way, a funny story that I heard is that Dusa and Felix, the authors of this book, this paper, they found these values: 2, 5 halves, 13 fifths, 34 over 13, and they couldn't quite figure out what they were, why they looked familiar, and then they were, or one of them maybe was talking to a colleague, I think Dylan Thurston, Bill Thurston's son, and he said, "Oh, well, those are Fibonacci numbers," and so that's how they found out. Okay, so so there's a couple of questions that come out of this. So one of them is this infinite staircase behavior a characteristic of this function, or is it a characteristic of the target, the ball? Because you can define the same function, but replace the ball capacity lambda by a lambda scaling of some other symplectic manifold X, where by scaling I mean that I scaled the symplectic form. And then you can ask, okay, so what does this function look for other targets other than the ball? And it turns out that in general, the function is piecewise linear when it's not equal to the volume constraint. So exactly what we saw in the other example. And we say that it has an infinite staircase if it has infinitely many non-smooth points. So that's just what I'm going to mean when I say infinite staircase. Okay, so the question is, does it always have an infinite staircase? If yes, why? And if not, when does it and when doesn't? and why is that? So since that paper of Macduff and Schlenk, there were other infinite staircases that were discovered. So on the for other targets, so the polydisk by Frankel-Muller, these three ellipsoids by Christopher Gardner and Kleinman. Then this is the one that I'm going to be talking about. Usher, I will also mention for certain polydisks. I'll say all these words again later on. So if you don't understand, if you don't know what a polydisk or a Higgs-Book surface is, it's fine for now. I'll also talk about this one if I have time. And then in the related work, Casals and Vienna did it for some of the same as here. Okay. All right. So with Dan and Tara and Alessia, the first result that we proved was this staircase obstruction theorem that says that if X is a closed toric symplectic manifold, or more generally convex toric domain with finite blow-up vector. So I don't expect you to understand all the words in this now if you're not from symplectic geometry. So let X be from a certain class of manifolds if the ellipsoid embedding function has an infinite staircase. So it might or might not have, but if it does, we know exactly where that infinite staircase has to have its accumulation point, okay, which is at so the X coordinate, I guess the A coordinate is going to be at A naught, which is a real solution of this quadratic equation. And the Y coordinate, or I guess the lambda coordinate, is going to be at whatever height the volume curve is at that point. So it might or might not have a staircase, an infinite staircase, but if it does, this is where it is. Okay, so there's a few things that I owe you after reading the statement of this theorem, which is explain what convex toric domains are and what toric symplectic manifolds are, possibly. Okay, the second one is sort of a silly observation. A quadratic equation usually has two solutions, and I say a real solution. So what's happening with the other one? I should tell you what pair and vol are. Also, just briefly talk about the volume curve again, which generalizes the red curve from the previous slide. And finally, the more important question is how good is this as an obstruction to the existence of infinite staircases? So, I'll start with the easy ones. So the solutions of this quadratic equation, if I call one of them A naught, then the other one is 1 over A naught. And if I have an ellipsoid of sizes 1A, and then I look at the ellipsoid of size 1 over A, and that's basically the same ellipsoid, just a scaling. And so this problem, this function, there's an involution that, A to 1A, you just sort of get the exact same graph on one side and on the other of the around A equals 1, just sort of compressed on one side and more extended on the other side. So for that reason, we just look at the function for A bigger than 1, because it's just a repeat on the other side and it looks much smaller. Okay, the volume curve. So this one is addressed. The volume curve. So I said if you have a symplectic embedding, which is part of the definition of the function, right, ellipsoid into a scaling of X, then it's volume preserving. So you get this inequality. Now this volume on the left-hand side is on the order of A. The other one's on the order of T squared vol. So T has to be bigger than or equal than square root A over vol. So that becomes our red curve in this example for X. Of course, I didn't tell you what vol is, but it has to do with the volume of X. So just bear with me. Okay, I'll skip ahead to how good is this as an obstruction to the existence of infinite staircases. Okay, so all right, what do I mean by this question? What I mean is, given X, I can compute A naught, and then, so if it were a perfect obstruction, we would say that this function has an infinite staircase if and only if when I compute the function at a naught, it is equal to, it intersects this red curve. It hits this red curve, this volume constraint, right? And it turns out, I should put question marks here because I was saying that's if it's like a perfect obstruction. So this side is what we prove in this theorem, and this side, sadly, the answer is no. Okay, so in these, oops, why did I choose T bigger? Oh, positive scaling. I chose a positive scaling, well, because I want the volume to be, well, I don't know what it means to scale the, I don't know what it means to scale the manifold by a negative number. So that's why. Thanks. Okay, so in these drawings here, you can see that here, so I computed what a naught would be for the ball. And then if I look there, indeed, C sub x of a naught is hitting that red curve. And indeed, there's an infinite staircase. And here, you'll see the C sub x. Oh, gosh. Why does it do this? I'm sorry. I swear this is as annoying for you as it is for me. Sorry, other way. No. Okay, as annoying for me as it is for you. And I don't know. Okay, so here it's, no. C sub x of a naught is different, right? It's not on the volume curve. Yara, I think this is what you were saying by some Zoom fails, but mine is like writing fail, but I really don't know what to do. So, and I only found out today. Okay, so, and here indeed there's no infinite staircase. Okay, but let me show you a case when it fails. So if the target x is equal to this ellipsoid, then a naught, which is equal to 3, you know, it is here C sub x a naught is equal to the right thing, but no infinite staircase, as you can see in the drawing. Okay, so however, it does seem that this can only happen when this a naught that we compute is a rational number. So maybe I should update this to, sorry, given x, compute a naught. If a naught is an irrational number, then there exists an infinite staircase if and only if C sub x of a naught is equal to n, right? In this direction, like I said, that's a yes. And this one is a maybe. So we haven't been able to prove this, but we have not found a counterexample. And we've looked, but we haven't. All right, so finally, the last two questions that I owed you from this, from reading the statement of this theorem. And also because I need this to be able to talk about the rest of the results. What are convex toric domains? And how do they generalize closed toric symplectic manifolds? So maybe I should say first, for those of you who are not symplectic geometers. So I said what a symplectic manifold is. Closed is, for some reason, the word that we use for compact. And toric means that it has, maybe I'll just say that it has as many rotational symmetries as it possibly can have. And that I'll leave it at that because it's not so important. So a convex toric domain, again, remember all my manifolds are 4-dimensional. So consider this function mu from C2 to R2 given by this. If you have learned some symplectic geometry, you might recognize this as the moment map for the action of T2 on C2. Also, I think algebraic geometers might recognize this as something, but I don't know the name of it in algebraic geometry. And a convex toric domain is simply the inverse image by this function of some convex region in the positive quadrant. Okay, so for example, if my convex region is a triangle here, then if I sort of use this and the definition of the function, now realize that this is a ball with capacity, the length of this side of the rectangle. And this one would be an ellipsoid, like I defined earlier. This one would be a polydisk, which just means a disk across a disk. And here each disk has area, this and that. This is also a polydisk, but a polydisk with disks of different sizes. And well, this is whatever it is. Yeah, I don't think it has a name. Okay, and why am I drawing only polygons and not like curvy convex regions? Okay, that's because that comes from the generalizing closed toric symplectic manifolds. There's this theorem, this beautiful theorem in symplectic geometry called the Delzant theorem that says that closed toric symplectic manifolds, what we get from it being a toric symplectic manifold is we get this map, again, a moment map, and the image of that. So moment maps always map to Euclidean space of a certain dimension. So for a 4-dimensional manifold, that would be R2. And the image of this map for any closed toric symplectic manifold is a polygon in R2 called a moment polygon, in higher dimensions, moment polytope. And so for that reason is why we're looking at, again, polygons for convex toric domains and not some other shapes. Okay, so this theorem is maybe not very, well, this theorem is just to say why they generalize also in this, in the context of these, this function is that if a closed toric symplectic manifold has the same polygon as a convex toric domain, then the ellipsoid embedding into one of them is the same as embedding into the other, which means you can sort of go back and forth between these two worlds. So if let me see, if I put up here the corresponding closed toric symplectic manifold, I'll just write here because if there are any algebraic geometers in the room, then you'll recognize these ones. Well, I mean, I'm sure you'll recognize what a ball is, but this one doesn't quite exist. This would be CP1 cross CP1. This is also CP1 cross CP1, and this would be a 2-fold blow up CP2, 2-point blow up of CP2. Okay, and finally, what are pair and ball? So pair of X omega is just the affine perimeter of this drawing. So for example, this ball has side length 1, then, well, because it's affine length, Euclidean length, that is also length 1, so pair 3, and the volume is 2 times the area, so vol would be 1. Okay. And then the way that this shows up, remember, was in the equation, I had this thing pair squared over vol, which in this case, I guess, would be 9. And this is an invariant of the shape, right? Because pair is linear with the scaling and vol is quadratic. So pair squared over vol is an invariant under scaling. Okay. So all right, so we're ready to talk about this next bit of the result, which is that a beautiful part of this story is when the polygons are scalings of lattice polygons. So for example, CP2 or the ball or the polydisk. And so we concentrated our study, our exploration on lattice polygons, and we found that there are infinite staircases in the ellipsoid embedding functions for each of these convex toric domains that are associated with these polygons. So this one here is the ball, and then here's an ellipsoid. Here's the polydisk. that other people had already found, and so on. So I should say, you don't have to worry. So you'll notice that I have these numbers here. You don't really have to worry about them. I mean, they have to do with how you construct. One way that you can think is how you construct the drawing. So 3 just says it's a triangle of side length 3. And then if you do :1, you chop off a little size 1 triangle from a corner. And there are more imaginative ways of chopping off corners than what I did here. But you'll see that to the same sort of blow up vector, you can have different shapes. And in total, we have 6 different blow up vectors. And in fact, that corresponds to 6 different functions. So if they have the same blow up vector, it's basically the same problem. Sorry. And you might, some of you might recognize this collection. These are reflexive polygons. So they're lattice polygons with exactly 1 interior lattice point. And you might recognize that there should be 16 in this collection, and I only have 12. So here's the other 4. But these don't have infinite staircases. We checked. In some sense, the manifolds are too small. Okay, and we further conjecture that among the lattice polygons, these are the only 12 that have these, and their scalings are the only ones that have an infinite staircase. But we have failed at proving this conjecture in generality. We've proved some particular cases, or people have proved some particular cases, but still eluding us. Okay, so these 6 staircases look like this. So you can see they're always piecewise linear when not equal to the volume constraint. We only care, in this paper, we only care about what happens before the accumulation point, which is why you don't see the part where it's just equal to the volume constraint. And one maybe interesting thing, you can see there's like 2 types of behaviors. In one, all these interior corners hit the red curve. And then in here, they all don't hit. And we don't quite know why this happens. I mean, we see in the proof why it's happening, but we don't know like the geometric reason behind it. Let me look at the time to see if I have time. It's okay. All right, so maybe I'll just try to say this slide very quickly before I move on to the next project. Okay, so how can we possibly prove that a Newton staircase exists? It's actually it's actually a very nice idea. I can say that because it's not my idea. It's also not how Macduff and Schlenk did it in their paper. They did it in a very painstaking way, which is an impressive work. But then later on, Felix explained to us how you could prove it with less work, and this is the way that we implemented. And so for these types of targets X, the ellipsoid embedding function is always, so we prove these properties. It's not very hard, continuous, non-decreasing, and has a certain scaling property. And then we just have to prove certain upper bounds and lower bounds for 2 intertwining sequences of numbers. Okay, so we prove that for a certain sequence of numbers, which is these ones in green, the scaling can't be any smaller than certain values. Okay, so that gives us, we're like finding an obstruction. And this is like, so we find an obstruction, we find a reason, a geometric reason for why you can't embed those particular ellipsoids into a scaling any smaller than these numbers. And for the blue sequence, we construct an actual embedding. So we take ellipsoids of these sizes, and then we actually construct an embedding into a scaling of the target X. And that shows, because remember the function was C sub X A equals inf lambda such that E1 A embeds into lambda X. So if you construct a certain embedding, then you've shown that the infimum can't be any bigger than that. Right? And so now after you have that information, for example, if you go from a green point to the following blue point, because they have the same height and the function is non-decreasing, you know that this has to be a horizontal line. And to go from a blue point to a green point, you use the scaling property. And it turns out that this has to be a straight line as well. And so that completely determines the function up to the accumulation point. All right, so, okay, so that's just reviewing that slide. That's the exact same slide. All right, so this is all talking about rational, lattice polygons, so what we call rational convex toric domains. But actually, there are, Mike Usher found that there were infinitely many infinite staircases as long as you took an irrational convex toric domain. So the convex toric domain that he focused on was a polydisk. So the shape is a rectangle with size 1 and beta, where beta can be any real number. And he found out that there were infinitely many values of beta for which this polydisk had an infinite staircase in its embedding capacity function. And this was the first such result. And also in its bibliography is this item, which that's the year of that reference, 628, Brahmagupta's Siddhartha. So he actually uses this really ancient, it's for like a way to generate, he calls them Brahmagupta moves. It's a way of generating, I think, numbers, giving a number. Anyways, it's sort of fascinating. I have never seen a paper with such an old reference. I was just very amused. And so then after that paper came out, we being all these people here, and I should maybe explain why we are all in the same picture, why we're all wearing a lanyard, and why we're all women. It's because this was at a research collaboration conference, of which there are many in different topics. Ours was in symplectic and contact geometry, and this is again, this is really great. So if you are a woman, or if you have any women students or postdocs, this is a really great thing to do. So what happened was, let's see, so Dusa was one of the organizers. Tara and I were asked to come up with a project suggestion, and then Morgan, Maria, Emily, and Grace were grad students, and I think they were all grad students at the time, and they signed up to work on our project, and then we were together for a week, in this case at ICERM in Providence in the US, and then we worked on it. So that's where this picture was taken, and then eventually this became a paper. So our project that Tara and I suggested was to try to find infinite staircases, but instead of for polydisks, for Hirzebruch surfaces, which are, and if you're an algebraic geometer, right, 1 point blow-ups of CP2, where the parameter B tells you how big that blow-up is. Okay, and so we found infinitely many infinite staircases, just as Mike Usher had done for the polydisk case. And we were really trying to understand the structure behind these infinitely many infinite staircases. All right, let me look at the time to see how much detail I can give. Okay, so I should almost be done. Okay, so we found 3 families of what we call blocked intervals. Oh, I should say what this line is. So this is aligned from b equals 0 to b equals 1. So at b equals 0, you have the CP2 case or the ball case. B equals 1/3 is one that shows up in that list of 12. This shape or scaling of this shape shows up there. And then I guess b equal 1, you would have nothing left. So we find 3 families of blocked intervals, which are intervals of b values for which that Hirzebruch surface cannot possibly have an infinite staircase. And then on either side of those intervals, for that corresponding b, you do have an infinite staircase. And for some intervals, let's see, for intervals on this side, so in 0 to 1/3, on the left endpoint, you have a descending staircase, which we had never seen before. So that's like the staircase is going like this to the accumulation point instead of going up towards the accumulation point. So if you're from in the blue or if you're an endpoint of a blue or orange interval, then the left endpoint has a descending staircase and the right endpoint has an ascending staircase. And on this side, you have the opposite. And you have sort of, you can see you have like more and more infinite staircases as b approaches 0.2 and more as b approaches 1. So that would be like a very long Hirzebruch surface. You actually don't have one at b equals 1/5. And I could tell you why this happens, but I'm not sure. Yara, when should I stop?
No, you can have some more minutes. Okay. I think you're almost done. Yeah.
Okay. So I just want to tell you how we what these intervals mean, and also why is it like ascending, descending on either end of the interval, and different from 0 to 1/3 and from 1/3 to 1. So I'm sorry, this is like the heaviest slide. So the embedding capacity function, remember, it was the infimum of the scalings, the infimum scaling of the target into which E1A embeds. But it turns out you can also define it as the max of the value, max over of the value of a certain family of functions. And these functions are called obstruction functions, and E's are these homology classes of exceptional divisors and blowups of CP2. So I will not attempt to explain what these classes are, but I'll tell you what the functions look like. So I have here a graph, a pretty busy graph. So brown, red, and purple are obstruction functions. So you see, they just look like they're like piecewise linear, and they get like squigglier and squigglier. They're like indexed by a number. So brown is the lowest number, and then red is higher, and then purple is even higher. And these obstruction functions occasionally poke out above the volume curve. So in this case, the volume curve is orange. It doesn't look very curvy because I'm very zoomed in, but they do. And so if I plotted all the possible obstruction functions, then I would just look at the maximum one, and there would always be one that is poking above, or if not, I would just be at the volume curve. Okay, and all right, so how does this give the intervals? Okay, so we know that if there exists an infinite staircase for the Hirzebruch surface, then the accumulation point has to be on the volume curve. So if there's an obstruction that pokes out above the volume curve at that A0, then there can't be an infinite staircase for HB, because the value of the function is going to be equal to the obstruction function which is poking out. And so we say that this class E is blocking that value of B. Okay, and then it turns out, because all the things depend continuously on the value of B, that if a class E blocks a certain value of B, then it blocks a little open interval around that value of B. So that's how you get a blocked interval. So here's this purple is a little snippet of an obstruction function, and here it is poking out above the volume and blocking at that B, right? So because it's going above A naught there. And on the right-hand side, prime here, then you see now it's poking above to the left, and so at the relevant point A naught prime, it's actually at the volume curve. So you can't have an infinite staircase coming from the left, an ascending infinite staircase, but you could have one coming from the right, and that is actually what happens unless A naught prime is a rational number. Okay, so that's how blocking intervals work. And finally, about it being increasing or decreasing on the left-hand side or the right-hand side of the interval, and that being different to the left of 1/3 and to the right of 1/3 just has to do with this function being increasing or decreasing. It's increasing on one side and decreasing on the other. And then if you just sort of run through the logic, you'll see that that means that it blocks staircases from one side or the other accordingly. All right. And finally, I think, I should say that in the meantime, Macduff and McGill have found a symmetry that acts on these classes, and that takes blocked intervals to blocked intervals. And so they've created even more blocked intervals. So now there's more blocked intervals, which I haven't attempted to draw. In all the intervals here, there's like a little, like smaller and smaller and smaller groups of families inside there. And in fact, then with together, the two of them together with Byler, they have found how you just need two of these classes, two of these E classes, and then there's an operation that you can do between classes that creates more and more and more classes. So you actually, to create all this very intricate pattern of blocked intervals and of infinite staircases, you need two E's, and then an operation that creates another class, and then you take one of the old ones and this new one, and you create another one, and then another one, and then another one. And then you use the symmetries, and you can create the whole pattern of blocked intervals and infinite staircases. Okay, and this drawing, I think I won't explain this drawing because it's not very important, so I'll skip that. Okay, all right, I'm done.
So I don't know if anyone has any questions, but just one question. I don't know, maybe it's, don't have any answer. Also, you said they don't know. In this when you told that you had this staircase, sometimes it's the volume curve, and sometimes it doesn't. Mm-hmm. Do you remember the slide? You said that it appears in the proof, but you don't have any geometric reason. So you can divide what are any kind of conditions that say something about that.
Yeah, so
some idea why that happens or not.
Yeah, so we don't, so I can tell you where it comes into proof. So when let's see, when we're finding these blue dots, these showing that a certain embedding exists, the way that we do it is, it's actually quite fun. It's called almost toric vibrations. So, and you do some mutations on almost toric vibrations. And what that means is, it means that you basically, so maybe you start with a shape, so say square, and then you can do like an operation where you sort of like cut it, and then half of it you leave the same, and then the other half, this half, you do like an affine linear transformation, and you move it so that this thing becomes a triangle. So you sort of like this side, you move it down, this side you leave the same, and that sort of tells you where this other side has to go, right? So then it becomes this thing, and then you do it again, and this becomes a thinner rectangle and a thinner rectangle. And what it turns out is that these rectangles, because you can turn, so I did the rectangle, sorry, because that's a polydisk is a square. So this should have been a square, sorry. You start with a square and you start doing these mutations and you get thinner and thinner triangles, which are also the shape of the ellipsoids. And an ellipsoid, the drawing for the ellipsoid is a triangle. So because you can do this mutation to the polydisk, it will mean that you can put thinner and thinner ellipsoids into it. And so each one of these drawings is going to give you a blue point in this slide of the proof.
Okay.
And in these 4 that hit the volume curve, once you do the first mutation, you're going to get a triangle in the drawing. So the ball starts off as a triangle. So if you have a triangle, you'll also always remain a triangle. This one there's a rendition of this 311, which is a triangle. Let's see, there's a rendition of the 311, which is already a triangle. So this one's a triangle. There's a rendition here that's a triangle for the polydisk, and this one's a triangle. But these 2, no matter what you do, so this one, you start off with a shape that is like this. And no matter what you do, when you do a mutation, you get something that is still like this. So it's closer to a triangle, but you always have a corner poking out. So what that means is that you can put this triangle, that ellipsoid, you can fit it in there, but you always have a little bit of space left at the top. And so that space is what corresponds to this distance. So, sort of the reason why it doesn't hit the volume curve is because if you change the shape that you started with, you never get a triangle, which is like not a very sad, like it doesn't tell you what's happening in the geometry, right? It's purely like in the proof, you see why it's happening. But I don't know what it says about these manifolds. So, yeah.
No. Well, if I don't know, there's something that you ask here. If you don't have any other questions, ask me about this for fun.
Yes. Okay. So this is just something that was very fun. So I should tell you, when we were doing this, we had no idea what numbers we were going to find. So we started finding these staircases. Oh, this is very dirty now. We started finding these staircases, and we had no idea what sequences were going to replace the Fibonacci sequence or the odd index Fibonacci numbers for these other cases. So we had a program that computed an approximation of this function, and then it took a long time. We would let it run, and then we would look at the drawings or look at the numbers that it spit out, and then we would look at what, it would come up with not even fractions, right? It would give us like a very long decimal number. We would try to turn it into a fraction with low numerator and denominator, and then we would make up a sequence of integers with that, and then to try to identify what the sequence was, we would put it into the online database of integer sequences online. And then it would sometimes happen that only one sequence would come up, and we'd be like, okay, we found the one, and we would try to understand the math behind it. But sometimes it would be like, it would have 3 different sequences that fit this beginning that we found. And so it'd be like, okay, we need to run the program again for another like 2 or 3 hours to find more steps in the function. But so once we only found one sequence, we were very excited. But then we went to read. Oh, can I not zoom in? Okay, so I don't know if you can read. I thought I could zoom in, but apparently I can't. Mm-hmm. So this was the sequence that showed up. It says, so 2, 5, 8, 11, 13, 15, 30. And these are the numbered stops on the Market Frankfurt Rapid Transit railway line in Philadelphia, Pennsylvania. So this is the first ever application of symplectic geometry to public transportation.